Okay, so let's take a look at your Unit 3 exam. And it's been a little while since I've done this, so hopefully it'll all come back to me. But the first page was some kind of quick questions about thermodynamics. Thermodynamics standard conditions are 25 degrees Celsius, 1 bar pressure, which is approximately 1 atmosphere. So I think I gave you credit for pressure of 1 atmosphere, 1 bar. These were each worth 1 point apiece. State function is a function that depends only on the initial and the final amounts, and then of course the change in that value is always final minus initial. It's what we call independent of path. Letter C, I kind of went with closed and isolated systems being synonymous in that there is no escape or influx of energy or matter between your system of interest and the surroundings. Question D, if your heated reaction is negative, that must mean that it's exothermic. If your heated reaction is positive, that must mean that it's endothermic and that it requires energy. So E requires energy. For F, you could have worked it a couple different ways, but I gave you 2 metals, copper with a specific heat of 0.385 and aluminum with a higher specific heat of 0.897. And if you zap them with the same amount of energy, the question is which one will have the higher temperature, and it's the one with the lower specific heat. So it's less stubborn to heat up, so copper is the answer there. Question G, identify one physical phase that is exothermic. So exothermic would mean that bonds are being formed. So that would be condensation, freezing, or deposition if it's skipping the liquid stage. H, identify one physical phase where bonds are being broken. That would be melting, evaporation or vaporization, same thing, or sublimation when it goes from a solid directly to a gas. I, which physical phase has the least amount of kinetic energy? That would be something in its solid state. J, which physical phase has the greatest amount of motion, i.e. kinetic energy, and that would be gas, something in its gaseous state. For number 2, these were each worth, let's see, looks like 4 points apiece. For A, the question was if you have a system that is gaining 133 joules of energy and the system, let's see, the surroundings, and it does 248 joules of work, then this is kind of the situation we have where the change in energy of the system was going to be equal to the change in energy plus the work done, and in this case the work done is negative. So we go ahead and sum that up and we get negative 115 joules of energy would be the change in the internal energy of the system. Question B, you're supposed to find the specific heat given this mass, this energy it's zapped with, and this change in temperature. So Q, which the energy was zapped, that's the 19.5 joules of energy is equal to the mass that which is given, specific heat you don't know. The delta T, of course, you find final minus initial, so the delta T is 10.9 degrees Celsius. If we arrange Q is equal to MC sub P delta T, we get C sub P is equal to Q divided by the mass, also divided by the change in temperature. And so you'll get the specific heat is 0.190 joules per gram degree Celsius. The next one, C, given the heat of vaporization of cyclobenzene is 30.0 kilojoules per mole, that must be what? Well, it should be endothermic. It's positive. How much energy is needed to vaporize 25 grams of this compound? So remember, we can unpack that 30.0 kilojoules per mole, and that means 30.0 kilojoules per mole. We're going to use that to our advantage if we make our first term the mass of the cyclohexane we want to vaporize, that 25.0 grams. Then, of course, we're going to need to use the molar mass to get it into moles. So up here I show the molar mass calculation, and then we insert the heat of vaporization. Rounded to 3 significant figures, I get 8.91 kilojoules of energy. For D, could have worked it a couple different ways. We're looking, so you're given the decomposition of O3 into O2 by, this is your kind of what I use as a puzzle piece, and the heat of reaction is given. And then you're supposed to come up with the standard molar enthalpy of formation of O3. So right here, we kind of talked about how to do this. Right here is the the formation of 1 mole of O3 from O2, and you'll need 3/2 O2 moles of O2 molecules to make that happen, to form 1 mole of O3. The heat of reaction of interest that's what we're after. That will be the standard molar enthalpy of formation of O3. So if we look at our puzzle piece up here, notice that if we reverse it and take it times 1/2, then we get the equation of interest. So here I am taking this heat of the reaction that was given, this decomposition O3, I'm taking it times a negative 1/2 to get the standard molar enthalpy of formation of O3, which is plus 142.3 kilojoules. Some of you did it differently, and it's pretty cool how you did it. So then we have a bunch of questions that are each worth 6 points apiece. In this case, we are given this balanced equation, and we said for this balanced equation, the heat of the reaction, it's exothermic, right? Negative 906.2 kilojoules. So the question is, what if we go ahead and have 45.0 grams of NH3, what energy will be released? And it was really kind of straightforward. So we'll need to convert those grams to moles using the molar mass of NH3 right here. So our first term is the mass of NH3, then we use the molar mass of NH3 to get to moles, and then we use right here, this is the energy released per 4 moles of NH3. So some of you didn't, you did well, but didn't quite catch that. So let me know if you have any questions about that. But round to 3 significant figures, the energy released burning or reacting 45.0 grams of NH3 must be negative 599 kilojoules of energy. On to the next one, Hess's law problem. So up here, this is the equation of interest. These are our 3 puzzle pieces, and yes, you had to work all of your work, show you all of your work below this line. So notice that to compare the equation of interest to the first equation, let's see, what did I focus on? Looks like maybe I focused on the NO2. Notice that we have 1 mole of NO2 in both the equation of interest and our puzzle piece, so we're just going to leave it the way it is. So actually I say 1 prime is equal to 1 basically, and write down the heat of that reaction. For the second puzzle piece, it looks like I concentrated on let me see. It looks like looks like I concentrated on the fact that I introduced O3 here, but there's no O3 up here in the equation of interest. So I'm going to have to use this to my advantage to get rid of my O3. So to get rid of my O3, I'm going to reverse it and take it times 1/2. I hope that works for you. So here I am reversing it and taking it times 1/2. Of course, then I need to take the heat of the reaction times a negative 1/2, so I get a positive 142.3 kilojoules of energy. Then for the last one, it looks like I'm back to, if I concentrate on the oxygen, okay, notice that the oxygen is on the wrong side, so I have to reverse it, and it's also 2 times too much, so I have to take it times negative 1/2, and that's what I did here. So then you'll get this puzzle piece, and then this is the heat of that new of equation 3 prime. And then don't forget, in a Hess's law problem, you always have to go ahead and you have to go ahead and it's funny. You have to go ahead and add these up. So notice that a couple of terms cancel, which they need to, but I do get my equation of interest right here. It's kind of got a mind of its own. It was doing so fine. So if that's the case, then I can go ahead and take these 1 prime, 2 prime, 3 prime heats of reactions, add them up as I've done here carefully. And as we're adding, remember now we can round according to decimals, and we get negative 304.1 kilojoules of energy. Very good. So now the next one, we were coming up with the heat of this reaction of interest using their standard molar enthalpies of formation of the products and the reactants. So remember, it's always the summation of the products minus the summation of the reactants. And don't forget that there's a little, we have to include from the balanced equation the stoichiometric coefficient associated with the product or the reactant. So the product side looks like this. We have 3 moles of HCl. The standard molar enthalpy of formation of HCl was given, negative 92.3. Plus, also on the product side, we have 1 mole of CHCl3. Its standard molar enthalpy of formation is negative 103.1 kilojoules of energy. So add those together. On the product side, we're up to negative 380.0 kilojoules of energy. On the reactant side, we had 1 mole of CH4, and its standard molar enthalpy of formation was given, negative 74.8 kilojoules. And then we have 3 moles of Cl2, but like the information given, remember, we know that anything in its standard state, in its standard form, the standard molar enthalpy of formation is 0. So I get negative 74.8 kilojoules of energy there. So then I take the summation of the products minus the summation of the reactants. And here's where you had to make sure that you kept your negative sign here. And remember, we're subtracting a negative, which what makes it into a positive. So then using the standard molar enthalpies of formations of the products and the reactants, we get for this reaction, the heat of the reaction is negative 305.2 kilojoules of energy. Then we move on to this one, where, trying to remember what I did. Okay, so here we actually have a system in which you are going to dissolve ammonium nitrate, and then that ammonium nitrate is going to cool your water down. So we actually can say that within our system we have 2 things going on. We have the dissolving process of the ammonium chloride, and then we also have the cooling down of the solution. But if it's isolated, then the change in thermal energy of the system is 0. So that means that the change in thermal energy associated with the dissolving process is equal to negative Q of solution. So we were able to track the change in thermal energy of the solution, and it's equal to mass, the specific heat of the solution, which was given above the change in temperature of the solution. So the mass was given. Now remember, for the mass, we had to be careful and include the mass. I did it right up here. We had to include the mass of the salt, the 1.20 grams, plus the mass of the water, 24.0 grams. So that mass goes right there. The specific heat of the solution, 4.1 joules per gram degree Celsius, and the delta T is negative 3.9 degrees Celsius. So the change in thermal energy of the solution was negative 4.0 times 10 to the second joules. So that means then the Q of the dissolving must be a positive 4.0 times 10 to the second joules. So then you had to go ahead and give this an energy per mole of NH4NO3 that was dissolved. So we need the molar mass of the salt, given right here, 80.05 grams per mole. So then right here, I said we had that amount of energy, that 4.0 times 10 to the second joules per 1.20 grams of the compound. This term right here is the molar mass of the compound. To get it joules per mole of compound, and this right here is one of the things we've been doing to get it to kilojoules per compound, mole of compound. I had to take 1 kilojoule over 1,000 joules. We're allowed 2 significant figures. We get 27 kilojoules of energy per mole of compound. Then we go on to the most interesting one. It's funny because if we compare this last 6-pointer with the first 6-pointer, this one's a lot more complicated than the other one, right? So what we have here is we have a certain mass of ice, 9.0 grams of ice, that is going to be added to coffee. Now we have the initial temperature of the ice, which is colder than freezing, negative 10 degrees Celsius. Of course, the freezing point temperature given up here, the transition temperature is 0. So this is colder than the freezing point. And it's going to be submerged into the coffee, which actually, here it is. The coffee's initial temperature is 90.0 degrees Celsius, and its final temperature after all of this ice is going to melt. We didn't know that till you read this. All this ice is going to melt. The equilibrium temperature, the final temperature of your coffee, is 78.2 degrees Celsius. So we have a few things going on. By my count, what's happening here is all of this. So within your system, we have that cold ice needs to go to 0 degrees Celsius. That ice needs to melt. And then that 9 grams of ice needs to go ahead and warm up to that equilibrium temperature, which was 78.2. Meanwhile, your coffee is going to cool from 90 degrees Celsius to 78.2 degrees Celsius. So I have little asterisks here in my answer key to show you that we're going to use Q is equal to MC sub P delta T for 3 of these things. The ice warming, that water, that melted water from the ice now needs to warm to the equilibrium temperature, and of course the coffee is going to cool. This term right here with the ice melting, we're going to use simply the mass of the ice, that 9.0 grams, times the heat of fusion that's given right here, 333 grams of energy are required per 333 joules, of energy are required for each gram of water that melts. So let's go to it. So here you can kind of see I've calculated my delta T's that I need. The delta T of after the ice melts and goes ahead to the equilibrium temperature is that 70, the final minus initial. So the equilibrium temperature, 78.2 degrees Celsius, minus the initial temperature right after it's transitioned, which is 0.0 degrees Celsius. There's my delta T. Delta T of coffee, of course, is negative 11.8 degrees Celsius. Then here I've gone ahead and started calculating the Q's that I can. So the Q associated with the ice warming is the mass of the ice times the specific heat of ice, which was given in the table. Remember, it's not 4.184 joules per gram degrees Celsius, it's 2.06 per grams degrees Celsius. And the delta T of the ice, and so we have energy required, 190 joules. Here, this term is what energy is required to melt the ice, and it's the mass of the ice times the heat of fusion of the ice. So we have 3.0 times 10 to the third joules of energy is required to melt the ice. Then for that ice to warm up to the equilibrium temperature is right here. Now it's that 9.0 grams, and now of course now it's in its liquid stage, so we use the specific heat of water, which is 4.184 joules per gram degree Celsius. The delta T is 78.2 degrees Celsius. So the energy required there is 2,900 joules. And then we move on down to what's happening with the coffee. So the coffee, we said, is cooling down. The mass of the coffee is our variable. We don't know that. We know the specific heat of the coffee used the same as water, 4.184 joules per gram degree Celsius. The change in temperature from its equilibrium temperature minus its initial temperature is negative 11.8 degrees Celsius. So we end up with the coffee, the change in energy of the coffee still has a variable. So the mass of the coffee times, if we take these two times each other, notice that the units of degrees Celsius cancel. So we have negative 49.4 joules per gram. So now we go ahead and start to add them together. So right here we have this term, the 190 joules, that's the amount of energy required for the ice to warm. That 3.0 times 10 to the third joules, that's the amount of energy associated with the ice melting. That 2,900 joules, that's the energy associated with that little 9 grams of water heating up to the equilibrium temperature. And then we have this last term, the mass of the coffee, which is unknown, times this negative 49.4 joules per gram. Now this is all equal to 0, so I combine these joules terms and I get 6.1 times 10 to the third joules. Plus, again, I'm going to carry my variable coffee times that negative 49.4 joules per gram. If I move, what did I do? If I move, let's see, how did I do that? I must have gone ahead, and if we move this to the other side, and then divide by, multiply by 1 gram over negative 49.4 joules, then notice units of joules cancel. This is actually correct algebra. And then we end up with units of mass and 2 sig figs. The mass of water that must have gone ahead and interacted with that ice at that temperature to get to that equilibrium temperature must have been 120 grams of coffee. So, did I say mass of ice? I meant mass of coffee. So, in this problem, if you gave me 3 sig figs, I counted it right. So, let me know if you have any questions.